Now, in this problem, we're going to talk about frictionless bank curves. And the frictionless bank curve is a very limited style of problem. And that's because the frictionless bank curve only results in one equation. And the main purpose of a frictionless bank curve is to establish a critical value for doing problems which include friction. And we're not going to look at those kinds of problems, or at least we're not going to look at it intensively in any depth. It's mostly going to be a conceptual treatment of friction on banked curves. Now, the shape of a frictionless bank curve is like a circular NASCAR track. A banked curve is basically a ramp which forms a complete circle, and you're driving around the perimeter of that circle. Now, most of what we're going to be doing in this particular video is really just showing you how we get the equation so that you have a better context for understanding these types of problems, which should allow you to better evaluate concept questions and maybe eventually one day actually have to work problems which involve banked curves, which do include friction. We are going to practice some of these problems, but like I said, it's a very limited style of problem because we only really have one equation that we work with. Now, taking a look at the frictionless bank curve, we're going to set this up really just like we do for a ramp problem. So we have a ramp which makes an angle of theta. Because it's a frictionless ramp, we're not going to have to worry about friction due to the one touch that we do have. And the one touch that we do have results in a normal force which is pointing perpendicular to the ramp. And then we have the force of gravity which is pointing straight down. Now, typically whenever we do ramp problems, we tend to find the components of gravity which are perpendicular and parallel to the ramp. But that's not going to be the case whenever we do frictionless bank curves. And that's because the acceleration for the circular motion is going to be pointing towards the center of the circle, and the circle is going to be parallel to the ground, not the ramp. And so a centripetal points parallel to the ground. Now, when you set up a force problem, it's always in your best interest to set it up so that one of the axes of your coordinate system is parallel to the acceleration. We talked about that before. And so instead of doing a rotated coordinate system, which is parallel and perpendicular to the ramp, we're going to do a coordinate system which is parallel and perpendicular to the ground. Now, normally we would call this the x dimension, and vertically we would say it's the y dimension. But again, this is circular motion, so we're going to use the RTZ coordinate system. So the radial dimension is going to be pointing parallel to the ground, and the z-axis is going to be perpendicular to the ground. So what we're going to do here is that instead of putting gravity so that it's got perpendicular and parallel components, it's actually the normal force which has components in our new coordinate system. Remember, we're looking at a coordinate system that's like this. This is the radial dimension, and that's our z-axis. So what we have is the normal force in the radial dimension points that way, and then we have a normal force in the z-axis which points that way. So this is Fnz, and this becomes Fnr for the radial dimension. Now it should be clear that this is going to be the angle theta right here, and that's because these are similar triangles. It becomes pretty obvious. But just like we did before with ramps, you can determine what that angle is supposed to be just using some geometry. So let's go ahead and set up our problem now. First, we're going to analyze what's going on in the radial dimension. And so for the radial dimension, what we have is this for our FBD. We have Fn radial, which points towards the center of the circle, is equal to m times a centripetal. Now, that's all we have is just that one force. It is not negative because it's pointing towards the center of the circle. In our old coordinate system, it would have been negative because it was pointing left. But you see, we're pointing towards the center of the circle, and that's what matters. So it's actually in the positive dimension. So we have Fn radial is equal to ma. And in order to get this in terms of Fn, which would presumably be a known quantity, what we're going to do is the radial dimension is going to be the sine function because it's opposite our angle. So Fn radial becomes Fn sine of theta, and that's going to be equal to m times v squared over r. Okay, now we're going to have to go to the z dimension, or the z-axis, and in the z dimension we have two forces. Here's our working FBD. We have Fnz, Fg, and then this is Fnr. Okay, so in the z dimension we have Fnet is equal to ma, or Fnz minus Fg is equal to 0 because in this z dimension it's in equilibrium. Now, the z-axis, or that z-dimension, follows the normal sign convention. So up is going to be positive, and down would be negative. And that's how we get Fnz minus Fg. So Fnz is this side of our right triangle. And so that component's going to use the cosine function. So we would just write Fn cosine of theta is equal to Fg. And so we need to eliminate Fn, and the way we're going to do that is by solving this for Fn. So we're going to get Fn is equal to mg divided by cosine of theta. And so we're going to substitute all of this stuff here in for Fn there. Okay, so let's finish this, and we're going to get mg over cosine of theta times the sine of theta is equal to m times v squared over r. Mass is going to cancel out of our equation. Sine theta over cosine theta is tangent theta, so we get g tan theta is equal to v squared over r. Or the common way of writing this equation is v squared is equal to rg tan theta. And this is the frictionless banked curve equation. Like I said, we're not really going to be able to do much with this because the purpose of this is to do one thing only, and that is to establish what the critical value for the velocity needs to be so that you would move in a perfect circle going around a frictionless bank curve. Now, it should be obvious from this equation if we solve this equation for r, the radius. Then we're going to get the radius is equal to v squared over g tan theta. All right, now my point out of this is simple, that if you're going faster than the critical velocity, then the object is going to move towards the outside edge of the circle. It's going to go up the ramp, in other words, until it finds a happy place of equilibrium. if you're going slower than the critical velocity that we establish over here, if you're going slower than that, then it's going to slide down the ramp so that our function works out. So r is going to change dependent upon v. Okay, so if you're going too fast, you go up the ramp, and if you're going too slow, you go down the ramp. And that's the whole idea behind the critical velocity on a frictionless bank curve, because if this is not frictionless, if we actually have friction, then the friction force can point up the ramp or down the ramp. So let's just take a look at, conceptually, a real quick example of what I'm talking about. So we have the ramp here, here's the object, and it's no longer a frictionless ramp. The car or object is moving. Let's say it's a car, and let's say the velocity of the car is equal to 25 meters per second, and we have our angle theta. So what we do is we calculate V critical, and we determine that V critical is equal to 20 meters per second. So in terms of friction, what this means is that the car is moving too fast for this critical velocity. So the car wants to go up the ramp. The motion of the car is attempting to go up the ramp. Friction is going to point down the ramp to maintain this location in space, unless the force required to keep it moving along this line exceeds the static friction force. So the force of friction would point down the ramp in that case. Now, if we determine, let's say the velocity of, or actually let's just say that we determine the critical velocity to be 30 meters per second. Well, if the critical velocity is 30 meters per second and the car is moving at 25 meters per second, then the car is attempting to slide down the ramp, and friction, to keep it from sliding, it's going to point up the ramp. And so that's how we use the critical velocity whenever there's friction on the ramp. So again, the whole idea behind the critical velocity of the frictionless bank curve is to do nothing more than allow us to determine which direction the friction force is pointing.